Welcome to my YouTube channel. I am Thalitakum Hutajulu from Udayana University Mechanical Engineering student. So the purpose of this video was made to fulfill a linear algebra course assessment, also to educate about linear algebra. Okay, this is my reference. My reference from the linear algebra, Kuldeep Singh linear algebra step by step. So from this book. So we want to learn about the eigenvalues and eigenvector. So the content from the bab, from the chapter is the 1. Introduction to eigenvalues and eigenvector. 2. Properties of eigenvalues and eigenvector. 3. Diagonalization and diagonalization of symmetric matrices and singular values decomposition. Okay, in the chapter 1, subchapter. Okay, introduction to eigenvalues and eigenvector. So definition of eigenvalues and eigenvector. We have example. So from the example, we have get the definition of the eigenvalues and eigenvector. So this is A. 4 means 2, 1 and 1, and U is 2 and 1. Then the evaluate AU. So we have multiplication. We have this is a formula. So this is and this is we multiply. So we get the 6 and 3 and equal to the 3 times 2 times 1. So this is application in the coordinate cartesius. So for a non-zero vector u, the scalar lambda is called an eigenvalues, and the matrix A and the vector u is called the eigenvector belong to or corresponding to the lambda, which satisfy AU equal lambda U. So this is a eigenvalue, and this is a lambda. So this is example 2. So from the example, we have the A, matrix A is 1, 1, mean 2 and 4. So A, lambda 1 is 2, lambda 2 is 3. So we make like pre-false. Whatever, and we have this is, and B we have this. We have example 2. So from the example we have this. Okay, characteristic equation. So characteristic equation is the determinant A mean lambda matrix identity equals 0. So the procedure of determining eigenvalues and eigenvector is 1. Solve the characteristic equation for the scalar lambda, and 2. Of the eigenvalues lambda determine the corresponding eigenvector u by solving the system. A mean lambda times matrix identity times u equals 0. This is example. And we have to see in the slide. So we have the matrix A threefold the eigenvector u because A times U equal 3 times U. This is example 2, so I have many example. So solving this equation give this eigenvalues lambda 1 equal 4, lambda 2 equal mean 5, lambda 3 equal 3. So this is a eigenspace. If A is an n by n matrix with an eigenvalues of lambda, then the set S of all eigenvector of A belong to lambda together with the vector space. 0 is a subspace of Rn. Or like, so S equal 0 is an eigenvector belong to lambda. So this is a S or subspace or set S. So set S is the O from U V or A times U plus C times V is the there is in S. Okay, summary. So from the subchapter we have the known that A times U equal lambda times U. So matrix A scalar multi eigenvector U by lambda. So eigenvector U are found using A means lambda times matrix identity and times U equals 0. Properties of eigenvalues and eigenvector. So this is a multiple eigenvalues. So this is a example. This equation. So from the equation we have the number of roots. So equation number 1. We have the number of root is the 5 because this is a 5, and number of root from the equation number 2 is the 12. So number 3 is the 101. This example, we have the A, matrix A. So what we do first? Okay, this is a note. This application in the coordinate or space, eigenspace. We said it plane is our eigenspace. So that we have a plane rather than just a line because we have two basis vector as so above which span the plane. a set of base vector B of the eigenspace A2 are given B, the 1, 0, 0 and 1, min 3, 1. Eigenvalues of the diagonal of integral matrix. So diagonal matrix, regular matrix, and this is a triangular matrix. So B is actually called an upper triangular matrix and C a lower triangular matrix because this is a 0. 0 is the upper and this is a lower triangular. If an n by n matrix A is a diagonal of triangular matrix, then the equivalues of are the enters along the leading diagonal. This is example. So from the example we have the lambda 1 is the 5, lambda 2 is 8 and 9, lambda 3 is 6, lambda 4 is the 17, means 17. So we have to know that from this because this is a upper triangular. Properties of eigenvalues and eigenvector. So if m is a natural number, then lambda m is an eigenvalues of matrix M with the same eigenvector U. If the matrix A is invertible as an inverse, then the equivalence eigenvalues of the inverse matrix is the A inverse is the 1, lambda is the lambda inverse with the same eigenvector. So we have the matrix, eigenvector and eigenvalues. A is U and lambda. So AM is a power U and lambda M, and B is a inverse. The eigenvector is U, and eigenvalues is the lambda inverse. This is a illustration for the lambda equal to the matrix A double the eigenvector U like this. So this is entry the leading diagonal. Okay, we have the matrix A and the eigenvalues. So determinant of A, the lambda 1 times lambda 2 times lambda 3 times until 2 times lambda n. So eigenvalues is the product of eigenvalues. So trace of A is the lambda 1 plus lambda 2 until the lambda plus lambda n. Addition of eigenvalues. So we have this. So if find the determinant of the trace of A. So we have this. This is a formula. So we make like this is a diagonal matrix. Diagonal or leading the diagonal. So we have this 1 plus 1 plus 2 is the 4. So this is a hence this is 4 is the adding all eigenvalues. Hamilton theorem. So this is a theorem every square matrix A is a root of the characteristic equation, that is P times A equals 0, where P difference the characteristic polynomials. This example. So from the example we have 0, A quadrat means 7 times A plus plus 6 times matrix identity equals 0. This is example 2. So from the example we have this. We can evaluate this. Example 2. Okay, summary. So the summary is every square matrix A is a root of the characteristic equation, that is P times A equals 0. The diagonalization. The goal of this section is to convert an n by n matrix into a diagonal matrix. The process of converting any n by n matrix into a diagonal matrix is called diagonalization. So n by n matrix to diagonal matrix. Similar matrix. This is example. We have A and V. So this is formula. The formula from determinant. Let's substitute to the A and V. So we have the 2, 0, 1, 2. Oh, 2, 0, 0, and 1. So and similar matrix A and B have the same equal eigenvalues lambda because lambda satisfy the equation. Determinant B mean lambda identity equal determinant A mean lambda identity is equal. Reduction to diagonalization. So n by n matrix A is diagonalization if it is similar to diagonal matrix T. This is a diagonal matrix because this is a 0, 0, and this is a diagonal matrix. Okay, we have example. So this is a diagonal matrix. So we have example 2. This is a matrix A. So with agent we make this is not diagonalizable, yeah. Not diagonalizable because min 2, 3, and 5 is not 0. So we have this. How to make a matrix A to the diagonalization. So U and V, step 1, step 2, and step 3. characteristic eigenvalues. This is a example. So we have been given the eigenvalues and corresponding the eigenvector of the matrix A. These eigenvalues of a matrix A, like the above, step by step. This example too. So A is a matrix diagonal. Power of matrix. So if T this is and Dm is the thesis. Okay, this is an example too. So D is the A is an upper trigonometric. So values are the entries of the leading diagonal of A. So this is a lambda 1, lambda 2, and lambda 3. Find to the A5. We have 2. This is the solution. Application of the power of matrix. So matrix power are particularly useful in Markov chains. These are based on matrix. These matrices are probabilities, and many real-life systems have an element of uncertainty which develop over time, and this can be explained through Markov chain. This is an example. And the summary, we have this. Okay, diagonalization of symmetric matrix. Okay, if multiplying this by p and by multiplying by p mean 1, give the factorization of matrix A. So we have this, and the equivalent eigenvector matrix P contains the eigenvector of A, and B contains the eigenvalues of E. From this we deduce that the power of matrix A can be found by factorizing A into the 3 matrix. This is a symmetric matrix. So the A-sequence matrix A is a symmetric matrix if AT equal A is transpose equal A. This is an example. So we have this, we have A diagonal matrix A. So we have the lambda. We have the lambda 1 is 5. Lambda 2 is mean 5. This is example 2. So we have the matrix key diagonally is the matrix A because key inverse key A times key equal D. So orthogonal matrix. If key is an orthogonal matrix, then key min 1 equal key times D. So we have this. This example. Properties of symmetric matrix. So let A be symmetric matrix if lambda 1 and lambda 2 are this day eigenvalues of matrix A, then their corresponding eigenvector of U and V respectively are orthogonal, perpendicular. So we have this. The dot product of eigenvector U and V is 0. Therefore, they are orthogonal. This example. Example 2. Orthogonal diagonalization. So in general, a matrix A is diagonalizable if there is an orthogonal matrix K such that this an eigenvector matrix K contains the eigenvector of A and eigenvalues. Matrix K contains the eigenvalues of A. So we have this. So A transpose equal A. As an example, procedure of orthogonal diagonalization is the procedure. The example step by step. The summary. Matrix A is orthogonally diagonalizable to A is a symmetric matrix. Singular value decomposition. Basic for a star vector space and basic for a finished vector space. This example. So from this example we have if V1 equal 3U and if V2 equal U. This is the application in the coordinate cartesians. This is same x and same axis. This is ellipse legs. Example. Introduction to singular value decomposition. We have this. So this A equal U times G times V transpose. So this is a min K rows and min K columns. This example. Example 2. So this is a application in coordinate. Example 2 is a proof of the singular value decomposition. So from this we have to know this. So from this to this. In summary, we can break any matrix A into a triple factorization. A equal U times D times V vector transpose. Okay, that's all of my explain. If I mistake, I so sorry. And finally, thank you for watching.